All right, so this section requires a visual going on here because what's going to happen is instead of finding the area of our region or the volume when we rotate it about some vertical or horizontal line, what we're going to do is take a region, in this case a circle, and we are going to picture it as being dropped flat on the ground. So we're going to drop that y-axis flat. And we're going to have what we call chords running across. You can see with the cursor me pointing at one of them. And what we're going to do is build up off of that and have it be the base of a solid. And it's going to be a base of a solid, kind of considered like a loaf of bread, where when you cut a slice, you know what the shape of the slice is. And I'm going to tell you for this demonstration purpose that these known slices are going to be squares. So I'm going to show you what they look like if I were to slice. And you can kind of see what's going to happen when I create the solid out of these infinitely many cross sections that are each having a width or depth approaching 0. And I build the solid up off of it, I get this dome shape. And it's this dome shape that I will be finding the volume of in this section. The only thing that's going to change is the base won't always be a circle. The cross sections won't always be squares, but the theory behind it will be the same. So let's show that solid one more time. It is this that we will be finding the area, the volume of. You will have a base on the bottom that will be a function or an intersection of functions. And you will be building up off that base with squares or triangles, or let's show it with triangles here for a second. So again, I'm going to drop that flat so the shape goes on the bottom. I'm going to picture chords slicing it. I'm going to picture triangles being built up off of it. I'm going to sweep them across the entire solid, and that's our integration process. It's going to create a three-dimensional structure that if you sliced it like a block of cheese, you'd be dishing up a bunch of equilateral triangles. Or actually, this one isosceles triangles, sorry about that. And the solid would look like this. And here is the shape sliding across that solid. All right, so keeping that in mind, I'm going to reset this. What we're going to be doing in this section is just that. So in your notes, for volumes of known cross sections, what I'm going to do first here is give you a little two-dimensional sketch. So we are going to have, let's go draw a nice big, some region created, and I'm just going to draw, on the demo it was a circle, but that's not going to be the case hardly at all. You'll have two functions crossing. I'll call the top one F and this bottom one in red I will call G. And we're going to picture shading that in, but we're not finding the area of it. We're not rotating it. We're going to drop it flat and build up off of it. And they'll tell you what your cross sections need to be, but they all will have as the base a chord as one of their sides. And so we're going to call this chord S. And what's going to happen is we're going to go and build up off of that. And we know that to get volume, we do the area times the depth, like length times width times height if it were a rectangular solid, or pi r squared for the area of a circle. Pull it up with the height to get a cylinder. But that theory is that we do area times depth, or area times height. Our depth is going to be called dx. So what I'm going to do is build up off of that, and let's pretend it was a square, and again I'm trying to draw 3D in a two-dimensional space, so that's why I had to show you that computer demo first. So picture building that up off of that, and picture me slicing it and giving you a slice. I'd be dishing you up a square-faced solid. That solid would have an area, which our book calls A of x, of side times side. That solid would have a depth of what we call dx. Would be its height. So really what we're going to have is an integration. We're going to run from A to B. We're going to dish up all those slices. Each one has a face area of A sub x and a depth of dx. x. So now what we need to do though is just figure out what that a sub x, a of x is. So on the top of this, let's write down what we know. First of all, s is going to be our side length. We'll always find it by doing top function minus bottom. Or if we have dy problems, right minus left. But these are almost always perpendicular slices to the x-axis. So you can be pretty safe doing top minus bottom. Also, what's going to remain the same is our volume is always the area times the depth. So we will always be integrating all of that up. So let's go talk about how it changes based on our shapes of our solids. So if I have square cross sections coming up off of here, the area of a square popping up on there would be side squared. So I just integrate from a to b, side squared dx. And again, to get the side length, I just do top function minus bottom function. If I was doing isosceles right triangles, and I'm not going to draw the x and y axes anymore, up off the base, then an isosceles right triangle with its leg across the base would pop up and out. Again, you got to picture these popping up and out of the screen, and that region is flat on the ground. And I'm going to slice it up like a block of cheese or a loaf of bread, and I'm going to hand you a slice. And your slice will be an isosceles right triangle with a little bit of thickness to it. But that thickness, as we integrate, approaches 0. The number of slices approaches infinity, and that's the definition of our definite integral. All right, so I'm still going to be integrating from a to b. The area of this face now becomes half of a square, or 1/2 of base times height. So what I end up having is a 1/2 multiplier out front on my isosceles right triangle with its leg across the base. If its hypotenuse is across the base, let's go draw like this, what it would look like. Again, isosceles have two legs that are the same, and when it's a right triangle, it means one of the angles is right. So when it's isosceles with the hypotenuse across the base, let's put a double on that. Okay, then these are my congruent sides, and the hypotenuse is represented by that S. And we could derive a formula, but I like to have you just look at it. Whoops, that doesn't look like a square visually. So let's go take a look at what we've got going here. For this one, when I had the leg as being on the side right here, I was half of a square. But when I put the hypotenuse across the base, then this is actually the side. And you'll notice I'm a fourth of a square. So what I end up with is a 1/4 multiplier out front. So I do 1/4 the integral from a to b, side squared dx. So those three are all similar. The square is s squared. Isosceles with the leg across is a half of s squared. And isosceles with hypotenuse across is 1/4. Oops, sorry, my phone's ringing. Just a second. I got to pause. Sorry, I had a phone call. All right, so let's go back and do our semicircles. Same situation going on here. So let me go ahead and get my bottom of my solid laying out. Still going to drop that chord. So picture that shape being laid on the ground, and it's got these chords. These chords are representing the diameter of a semicircle. So I'm popping those semicircles up and off the floor. Again, I'm going to slice it up and give you a slice. You'll be eating a semicircular faced solid that has a tiny little depth that we call dx. All right, so how would we get the volume formula for that? All right, my volume will equal the area of a face. So I'm going to derive it up in this corner, and then we'll decide what this multiplier will always be. So the area of a circle is 1/2 pi r squared. But my radius in this case is actually half of a side length. So you'll notice when I clean that up, I get 1/2 times pi times 1/4 times s squared. So a pi eighths multiplier comes in front on this one, and it'll always be pi eighths for a semicircle. So it might require a little memorization, but if you forget it, always go back and just have the ability and capability to derive it. Last up is the equilateral triangle. So let's do that. So this represents a side of an equilateral triangle popping up and out of the screen, dishing you a slice. You're eating an equilateral triangle. By the way, I've heard they're delicious. let's go take a look at what we'd have. Again, we're going to have a multiplier out front. I'd like to derive that multiplier for you as much as you might hate it. You just say, I just want to memorize it. Go ahead, but I have OCD and I'm going to go derive it. So the area of any triangle is 1/2 of its base, which we're calling S, times its height. And my height needs to be in terms of S. So when I cut an equilateral triangle in half, I create what's called a 30, 60, 90 triangle. And those always have the same relationships amongst the sides. All right, all of these sides are S, so this one's S. Right here, though, is 1/2 S. And you should have learned in your geometry classes in pre-calc and algebra 2 that the long side of a 30, 60, 90 is √3 times the short side, which for us is a 1/2 S, or √3/2 S. It requires a little remembering of your 30, 60, 90, or you could use Pythagorean theorem on it to get this and say 1/2 S squared plus x squared equals S, blah, blah, blah. You'd get it, and I would get √3/4 S squared when I clean this up. So my multiplier for the equilateral triangle is a √3/4 side squared dx. So notice, if you can get the side, top function minus bottom function, you're just going to integrate and sweep those across, and they all have a multiplier out front. All right, so let's go do a couple examples, and we'll be good to go. I don't want to do this one. Let's do, here we go. Let's drop that circle down, kind of like the one I showed on the computer demo. So this circle is laying flat on the ground, and I'm going to pop some shapes and cross sections up out and dish you up a slice, and we're going to add up all those slices. The first thing we need to do is get the length of a side, because each one of these is going to be popping up and out. First of all, it's going to be squares popping up and out, and I need to figure out a side length. It's top function minus bottom function. The problem is, this is, whoopsie, just move that off the center here. This is not solved for y, so I need to go do that. My y would equal 25 minus x squared, my y squared. So my y would be plus or minus the square root of 25 minus x squared. So what I've got up here, my top function represented by x comma square root 25 minus x squared. My bottom function is x negative. Boom, 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 ba-dum, bum, bum. All right. So when I do top function minus bottom function, I end up getting 2 √25 minus x squared, which should make sense because it'd be 2 of these, and that's this length. So however you get it, my side length for all of these problems, my s is going to be 2 √25 minus x squared. And all of these have an s squared in it. So maybe before I go do them all, I'll go square s, and I'd get 4 times 25 minus x squared. Let's begin. When I do the squares, I do the area of a face, which is a side squared, times its depth, and I'm going to integrate that from -5 to 5, or I could do twice from 0 to 5. Sorry, now someone came to the door. So where was I? I was going to say, oh, you could integrate from -5 to 5, or if you're going to be integrating by hand, it's easier if you maximize the use of 0 and use some symmetry. So you should do 2. And go from 0 to 5, and then you would just do half a loaf and double it, and you'd be good to go. So this is going to become 2 times the integral from 0 to 5 of s squared, which is right here, so I'm going to put a 4 out front, and then it would be 25 minus x squared dx. So that'd be 8 times, and you'd go integrate it. What if I was doing semicircles? Well, it would be pi/8 times, that would be my multiplier, the integral from -5 to 5 of s squared dx. Or I could go 2 times the integral from 0 to 5 of s squared. And again, I've already taken s and squared it over here, so that's where this is coming from. And I'd go math 9 that, but you might want to take your constants out front. That's going to cancel, so that would end up being pi times isosceles right triangles, and let's say leg across the base. What's that going to look like? Well, it has a 1/2 multiplier out front, otherwise it's basically just half of that answer. Equilateral triangles has a multiplier of √3/4, and then side squared, etc., etc. But it would just have a root 3 over 4 multiplier on the other one. So that went kind of fast, but we'll slow it up here for the next one. These are kind of easy if you get the idea of those multipliers. It really saves you some time. So let's go take this next one and get a good graph going of it, or a decent graph anyway. We've got y equals x minus 4, which looks like a line that goes like this, 1, 2, 3, 4. And we've got 4 minus x, which is coming in from a y-intercept of 4 and going like that. And x equals 0 is also. So this is my solid. It's the base of my loaf of bread. Kind of weird loaf, but that's the way it is. And I'm going to be popping up some squares, equilateral triangles, semicircles, and isosceles right triangles, and let's say on this one with the hypotenuse across the base. So first thing I do is I drop that side length down and I write an expression for it. It's always top function minus bottom function. My top function is x minus 4. My bottom function was 4 minus x. I lied there the other way around. Sorry. This one's 4 minus x. It's the one going downhill. This one is x minus 4. So my s is going to be top function, 4 minus x, minus bottom function, x minus 4. When I clean that up, I end up getting 8 minus 2x. That is my side length. And now I'm ready to roll. Because my squares, I'm going to be doing s squared dx. I'm going to integrate from 0 to 4. There's no symmetry, no doubling. I'm going to sweep them all the way across here. And I'm going to do s squared dx. And I should notice there's no pi's out front for this. I'm not rotating it and making washers or discs. I'm simply building up off of a base, a known base with known cross-sectional slices. You could integrate that by hand, by foiling and all that kind of good stuff, or you could do it on your calculator with Math 9. The equilateral triangle is going to pop them up off of this. It still requires that side squared, but remember there's a multiplier out front of root 3/4, root 3 over 4. And so it's going to be exactly the same as the answer from part A, with the exception of the multiplier out front. And again, you would go get a decimal for that by Math 9ing it. Semicircles, I'm going to pop semicircles up off of there, but there's a pi-8 multiplier. Now, if you don't remember that, watch how that would evolve just by knowing the theory behind it. So watch, we had, sorry, I'm going to go draw that again. We had our side length right here, and we were popping these up off of here, and that side length is the diameter of the circle. It's 8 minus 2x. So what happens if I were to do this by hand, because I forgot, is I would say 1/2 pi radius squared, and the radius would be 8 minus 2x over 2, because this is the diameter right here, squared. And you'll notice that when I have the 1/2 out front and the pi, and the squaring is going to bring out a 1/4, I get pi-8 8 minus 2x squared. So it does help to memorize it, so you're not going through that thought process and over and over and over again. Isosceles right triangle with the hypotenuse across the base has a 1/4 multiplier, because when that the legs are here and this is the hypotenuse, it's really a fourth of what you get over here. So once you have the answer for part A, you can multiply it by root 3 over 4 for part B, by pi-8 for part C, and by 1/4 for part D. All right, so last up, we're going to do a little muscle memory and see if we can remember how to do this last one. We're going to switch it up here a little bit. Example 10 in your notes, and then that'll be it for this section. And the assignment is worksheet 7-2B. And there's not very many on that assignment. All right, so now what I have is a horn, and we're going to toot our own horn here. Toot, toot. And the horn will have the shape of the solid bounded by y equals e to the point 4x. That's obviously this bottom one with some curvature. And the line is y equals x plus 1. And what I'm going to do is you would shade that in. You're going to rotate it about the x-axis, and I'm going to kind of draw what that would look like here. It'd have the green on the outside. Whoops, that's not the best, but some red on the inside. You'd shade it. It'd have a circular base, kind of look like that. So this would all be solid, solid with that empty. And let's have somebody go. Here's somebody's big mouth with a nose, eyeballs. There, that's what's going on. We're yelling through the horn. But I digress, because what am I supposed to be doing? That I was just getting into my artistic zone there. I'm supposed to find the volume of the material used to make the speaker. Well, let's go figure that out. I'm doing a rotation. I am whipping my representative rectangle, which is perpendicular to the axis of rotation. Let me make it a little nicer. My representative rectangle right here, it runs perpendicular to the axis of rotation. Picture that little piece of dental floss, and you're just whipping that around. And what it's going to make is those washers shapes. Looks like this, and we need to find the volume of one of those washers. So let's remember how we do that. Volume of a cylindrical washer would be pi times the radius squared. And we do big R, axis to the outer edge. So on my picture, my big R is from the axis to the outer edge of the solid, which is really just the y value on the green line, which is x plus 1. So my big R is x plus 1. My little r goes from the axis to the inner edge. Well, that's axis to the curve. And so it's directly just an e to the 0.4 x. So let's go whip that sucker around and create the solid. We do pi times, we're going to run this way. We got dx problem going, so we'd go from 0 to 3. Big R squared minus little r squared dx, where dx is the depth of each cylindrical washer. So I would do pi times from 0 to 3. Big R, x plus 1, quantity squared minus little r, e to the 0.4 x quantity squared with respect to x. I would go math 9 it. La 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 la. I would round to 3 decimal places. Yada yada yada. And that's it for today. Hope you learned a lot. Over and out.